Hello and welcome back from your Thanksgiving break. I'm going to assume that all of you now are experts at writing electron configuration and orbital notation, and hopefully finished that up yesterday. Um, I wanted to go through the rules that sort of govern the filling up the energy levels and those orbitals. So I'm just going to go through them kind of quickly. Electron arrangement in atoms, the rules that govern that. So first of all, electron configuration is the ways in which those electrons are arranged around the atom's nucleus. And we kind of already talked about the rules, but I just kind of didn't put names with them. So the first one is called the Aufbau principle. It states that electrons occupy orbitals of lowest energy first. And you actually already know that. And a lot of you even probably knew that from ninth grade physical science. So what we did uh, went into a little more detail on the shapes of those orbitals. We said, we have s orbitals that are spherical, and the first and lowest energy. So the lowest energy level fills first. So let's say that we have a nucleus in here. There's some protons and neutrons in there, but this is our 1s orbital. There's a couple of electrons, and then the second energy level is also spherical, and that's a 2s. And then we said it gets kind of crazy that there's this 2p. Whoa, sorry, my stylus is crazy. Isn't that just perfect? Um, but the 2px, 2py, 2pz, and so on. So again, that Aufbau principle just says, hey, the lowest energy levels have to fill first before any of those higher energy levels will fill. So first it's that 1s orbital, then it's 2s orbital, and so on. Okay, the next rule is the Pauli exclusion principle, and it simply states an atomic orbital may describe at most 2 electrons. So the orbital, so for an s orbital, right, here's my 1s orbital, and we said, oh yeah, 2 electrons in there. This arrow represents 1, and this arrow represents the second one. And then when we get to the p sublevel, we break that down into 2px, 2py, and 2pz. And again, only 2 electrons in each one of those. 2 electrons are, each can only hold 2 electrons. If it holds 2, we say that one is spinning in this direction, the other one is spinning in this direction. The third one then is Hoons rule, which states every orbital in a subshell is singly occupied with 1 electron before any one orbital is doubly occupied. And again, you already did that. We said if we're looking at, for example, nitrogen, which is 1s2, 2s2, 2p4, and we did the bubbles on the sheet that you just finished. But we could have done arrows, and we could have said, yeah, 1s, and there's my 1s2, and then 2s. And I did notice several of you when we were going through this were saying 1s squared, 2s squared. Like lots of you were saying that. It's not squared. This means 2 electrons, not that the 2s orbital is squared. It literally means this is the 2s, this is the 2s orbital, and it has 2 electrons in it, meaning that it's full. In this case, we would say the 2p sublevel because there's 3 orbitals in here. The 2p sublevel with 4 electrons in, but this isn't squared. Squared obviously has a different meaning than that. Anyway, so here's where Hoons rule comes in, and I think you're all experts at this already. We really did talk about it. but I just didn't have you write those rules down. But we said 1 electron in each one of these. Here's 2 electrons in the 2p sublevel, 3 electrons in the 3p sublevel, but nitrogen has 4. So then we go back to the first 2p, which is 2px, and we add that second electron. There's our 2p4. But the rules by which they have to be filled are very specific. And Hoons' rule says, yeah, we have to put, every one of these has to be singly occupied before we can put a second one in any of them. And again, you guys already. Okay, so first of all, I have to apologize. This is kind of a mess, but it's a PDF, so I can't erase it. So the quantum mechanical model, and we mentioned this a little bit before we started this whole process, but the quantum mechanical model says each electron has 4 quantum numbers. Okay, and this sounds complicated. I promise it's super simple. The first quantum number, so here's our 4 quantum numbers. The first one is just the energy level. So right here, the energy level. If it's a 1s, then the energy level is 1. If it's a 2s orbital, the energy level is 2. If it's a 2p, the energy level is also 2. So both of these are the energy level. So that's the second energy level. 3s is in the third energy level. So that's the first quantum number, just the energy level. Then the second quantum number is the shape of the orbital. And we said S, P, D, and F are all shaped different, have a different shape. The S orbitals are spherical. P, D, and F are all kind of dumbbell shaped, but slightly different. So those are the different shapes. So that's the second quantum number. We said there's 4. The third one is the orientation. Remember I said if we are talking about the 2p sublevel and we break that into 2px, 2py, 2pz, that they're on different planes. That's what the x, y, and z are. So for example, and I know this is a 2-dimensional drawing, but we would say, one of the p orbitals is, going up and down. Another p orbital is going, from left to right, like that's another plane. The third p orbital maybe is going from front to back on that plane. So they're all on different planes. So that orientation on what plane do those orbitals lie on. So orientation. And then the fourth one is spin direction. One is spinning this way, that's the 4th quantum number. And the other is spinning this way. So those are the 4 quantum numbers. And remember, the rule is that no electron can have the same 4 quantum numbers. Because even if they have the same energy level, they're the same shape of orbital, the same orientation of the orbital, they're going to have different spin directions, right? So they can have 3 out of the 4 that are the same, but definitely not no 2 electrons are going to have the same 4 quantum numbers. So this brings us to how are the quantum mechanical model and the Bohr model alike, and how are they different? So the Bohr model, remember, this is what you've been doing since middle school. There is a nucleus and it has protons and neutrons in it. And then orbiting around the outside, like planets around the sun, are those electrons. The first energy level holds 2, the second energy level holds 8, and so on and so forth. And so how are the Bohr model and the quantum mechanical model the same, and how are they different? Well, the Bohr model, the quantum mechanical model restricts the energy of electrons to certain values. And so the Bohr model and the quantum mechanical model do say there's energy levels here. Okay, so there's a lower energy level. Then there's a high, next highest energy level, and so on. So in that way, they're really a lot the same. We know or believe that, yes, there's a lot of proof that electrons do in fact exist in those energy levels. And so the quantum mechanical model, this newer kind of model, and that Bohr model both state that and both agree on that. The way that they are different is that the quantum mechanical model, the one that we've been working on with the S and P and D and F orbitals, does not specify an exact path that the electron takes. In fact, it says no, it's not like planets orbiting around the sun. It's this cloud and area of probability that is surrounding the atom, the nucleus of the atom. And the electron might be anywhere in this whole cloud, you know. And because the cloud is bigger right here, it's more likely going to be somewhere here than it is in this skinny pot spot right there, if that makes sense. And again, more likely to be found here in the larger part of the electron cloud than it is kind of in this skinny part. So it really says there's not really an exact path. Electrons are not that predictable, as it turns out, but that we think of it as more of an electron cloud. And that really recaps both the Bohr model and the quantum mechanical model. And we've been, just what we've been talking about with these orbitals over the last week is really that whole quantum mechanical model.